Hello. So this is the first lecture in a series of lectures on a course, which was formerly known as Math MTHE 334. And associated with this was also MTHE 335, which I will also be posting lectures for, just because I can. And these are courses on signals and systems. Okay, so 334 more or less is about signals, and 335 more or less is about systems. These are topics which are often covered in engineering courses, electrical engineering especially, but also the mathematical content is of interest to people in physics and also mathematics. In order to get started with talking about signals and systems, the first course in signals is best motivated maybe by thinking about systems. Okay, so to talk about signals, we're first going to talk about systems, and then we're kind of going to stop talking about systems for the most part. Okay, so what's a system? Well, a system is, kind of a black box which takes inputs like these and gives me outputs like these. Okay. And so we're not so much interested in this course in taking a specific system and a specific input and sort of calculating the specific output. What we're interested in thinking about is the system as a general kind of a thing, which takes a general class of inputs and produces a general class of outputs. And so therefore, what we want to talk about is we want to talk about not fixing an input and talking about its specific characteristics, but fixing a class of inputs, okay? And correspondingly, a class of outputs. And so we want to talk about spaces. Of inputs and outputs. Okay. Now, what attributes should these spaces have? And the best way to kind of motivate this is to think about attributes of systems, okay? And a common, well, you can debate about how common it is, but a popular attribute of a system is that it be linear. Okay, and what should a linear system be? Well, a linear system as a mapping from your space of inputs to your space of outputs should be a linear mapping. All right, and so one of the immediate consequences of that is that spaces of inputs and outputs should be vector spaces. Okay, good. All right, so we know what vector spaces are, and we're going to talk in a little bit of detail about specific kinds of vector spaces shortly, but certainly we need to have a vector space structure. What other kinds of attributes might a system possess? Well, a good attribute that any reasonable model of a system possesses is continuity. Okay, and what does continuity mean? Continuity means that, as a mapping from the space of inputs to the space of outputs, well, it's a continuous mapping. Well, as you know from your analysis course, there's various ways of characterizing continuity. There's epsilon delta definitions, and perhaps for our purposes here, because it requires kind of the least notation to say in a vague way, is to use a sequential characterization of continuity. Okay, so you remember what that looks like. So if we have a sequence of inputs, such that it converges, okay, then the sequence OJ of outputs and so these are not just random outputs, these are the outputs corresponding to the inputs. So OJ is equal to what you get from the system applied to IJ. Okay. This satisfies the property that the limit as J goes to infinity, OJ is equal to some O, and O, moreover, is what you get when you apply the system to the limit of the input sequence, I, okay? And so, this way of thinking about continuity says that the converging sequence IJ is mapped to the converging sequence OJ. And moreover, the limit of the output sequence O is the system applied to the limit of the input sequence I. Okay. So this implies that you need to talk about convergence. Okay, so to talk about convergence, we will use the structure of a norm. On the vector spaces of inputs and outputs. Okay, so I'm going to be assuming that in your analysis and or linear algebra course that you've seen the idea of a norm before. And in the context of an elementary analysis course, norms are usually put on the finite dimensional Euclidean spaces, Rn or Cn, and you talk about notions of continuity and convergence with respect to norms like that. All right, so in this course, we're going to be talking about signals, spaces of signals, so input signals and output signals, and these are typically not going to be Rn or Cn. These spaces of signals are going to be significantly more complex, and so the idea, so the issue of choosing a norm becomes non-obvious and consequential. Okay, so one of the things we're going to see is that you can take the same space of signals and put on it various norms, and that will have serious impacts on the kind of analysis you can do on the resulting normed vector space. Okay. And so the sort of punchline of this is that for the first half of the course, we're going to talk about normed vector spaces of signals. Okay, and we're going to see that there's lots of different flavors of these kinds of normed vector spaces, and they have different kinds of properties depending on what the space is and what the norm is. All right, so that's going to be the first part of the course. The second part of the course is Fourier analysis. Okay. And Fourier analysis is going to consist of discussing things which we will call Fourier transforms, and we'll see. And you know, in most representations of this subject, the way it's talked about is that the Fourier transform is one thing. In this course, there's going to be 4 Fourier transforms that we're going to talk about, depending on the kinds of functions of time that we're dealing with in each case. And you know, so. The idea of all of those transforms, and you may have seen the word Fourier sort of coming up in this kind of way before, is that you transform a signal as a function of time to a function of frequency. Okay. And the idea is that you take your you fix some signal which you think of as a function of time, and then you transform it some way by one of these Fourier transforms that we're going to talk about. And what you get back is a function of frequency, and the function of frequency kind of tells you at each frequency what the content of your time signal is at that frequency. And so let's maybe to get some intuition about this, let's think about 2 functions of time. Let's call them f and g. Okay. And f is, you know, kind of a nice gentle kind of a function, like so maybe. Okay, and g is less gentle. G maybe looks like that or whatever. Okay. And now what I want to do is I want to apply one of my Fourier transforms to it, which I will denote by the symbol script f. And the idea should be that your transform, Fourier transform, which represents sort of the frequency version of that thing, should, you know, be able to qualitatively distinguish between the kind of obvious differences in these 2 functions f and g. So I'll call frequency here omega. When we actually talk about transforms, we're not going to use omega, but omega you will have seen before as the variable for frequency. Okay. And so, you know, because the signal f, you know, is kind of gentle, what you expect is for most of the content of the, you know, the sort of Fourier transform of f to be at, you know, low frequencies. Okay, whereas G, you know, has some rapidly oscillating bits to it, and so you expect G to have you know, sort of maybe a broader Fourier transform, representing the fact that it has content at higher frequencies. Oops. Okay, and so the idea is that, you know, it's a bit thicker here at high frequencies than is the Fourier transform of f. Okay. All right, so that's going to be kind of the intuition behind the Fourier transform. So, but there's going to be some careful mathematics there, and so we should think about the kinds of things we want our mathematics to do. And so, generally speaking, what should the properties of a good transform be? Right. So we're going to be focusing on the Fourier transform. There's all kinds of other transforms, and in your differential equations class, you may have seen the Laplace transform. Okay. What should happen is that when you apply the transform, whatever your transform is, to a function, there should be something about the transformed function which which gives you information about the original function. Okay, so there should be information about f that is discernible from f of f. Okay, so it should be interesting, in other words, is kind of the way to say that. Okay, that's one thing you should see. Now, what's a very important property of a transform? Well, to kind of illustrate that, maybe let me think about a very dull transform, but one which you may like to have a whole course about, and that's the zero transform. So the zero transform takes a function f and returns the zero function. So that transform has one particularly nice property, which is that it's easy to calculate. Okay. And it certainly is very structured. The zero function has lots of structure. It's a very, very special function. And so, you may like it for that reason. But one significant defect of the zero transform is that it does not allow you to distinguish between two functions. So if you give me a function f and a function g and you transform them under the zero transform, you get the same thing. So it doesn't tell you which of the transformed functions is f and which one's g, and so this is sort of a rambling way to talk about an important attribute that any transform should have, which is that it should be invertible in some way. So there should be a unique transform associated with every function. Okay, and the way that most of the time we're going to see invertibility show up is not literal invertibility, it turns out, although in some important cases it is literal invertibility. But it's going to be a situation, and maybe this, our sort of system drawing up here is useful here. But let's think about the system here as being the transform, okay? Okay, sorry about that. I had a pen issue there that I've fixed. And so if we think of our transform as being our system, and the inputs are functions of time and the outputs are functions of frequency, we want this transform to be invertible. But what we're going to see is that for Fourier transforms, the natural class of output given some class of inputs, it's not true that this transform is actually invertible, and it fails typically to be surjective, but it's injective. And if you think about it, injectivity is all you really need, because injectivity means exactly that there's a unique transform that corresponds to every function. Okay, and so the point is we will consider injectivity of transforms. Okay, and we're actually going to put a little bit of effort into proving that the Fourier transforms that we talk about are injective. Okay, and for some of them that's going to be actually quite easy, but for others it's quite non-obvious that they're injective. Okay. All right, and so that's another important attribute of transforms, and the other is actually, so if you prove that your transform is injective, then that means that in a suitable way it's invertible, right? So if you have the transform of a function, you know that there is a unique function in the time domain that corresponds to it. Can you calculate it? Okay. And again, this is going to be something that's going to occupy us for quite a lot of the time. It's going to be kind of the major topic of Fourier transform theory. Okay. All right, so this is an outline of the content of the course. And so again, there's sort of two major components of the course, and there's going to be kind of a hard transition between them. One is going to be this normed vector spaces of signals, and then the other is going to be Fourier analysis. And we'll definitely see that there's a connection between the first part of the course and the second part of the course, in the sense that when you talk about Fourier transforms, you will normally require some properties of the input signals and some properties of the output signals. And so these normed vector spaces of functions are going to show up as the domain and the codomain of our Fourier transform. Okay, all right, so that's the rough introduction. Let's, to get started, think a little bit about signals. Okay, and so a signal is a function of time. Okay. So there's two parts of that simple statement that we should focus on. One, which we'll talk about just shortly, is what's the meaning of time. And the other is where should these functions take their values? So let's deal with the second one first. And so in this course, we're only going to talk about scalar valued functions. And that will mean that we're going to talk about functions which are either real valued or complex valued. Okay. And I will use the symbol F like so when I want to allow both of those possibilities. Okay. To be able, and so a little tiny bit of notation attached to the fact that we're going to be doing two things at once sometimes, to be able to talk about R and C at the same time. Okay, there's two bits of notation. If X is in F, meaning it's either a real number or a complex number, then I'm going to use the symbol X bar. And it'll be the complex conjugate. If F is C, and X bar is simply going to be X when F is R. Okay, so this is as it should be. Okay, and correspondingly, another thing which is a little bit different from the real and complex case, not much different, but enough so that I will point it out, is the norm or modulus or absolute value. And so in the complex case, this single norm symbol on each side here is going to represent the modulus in the complex case and the absolute value in the real case. Okay. All right, just so I can freely use those symbols without having to worry about whether it's F or C. Okay, all right, so good. So signals are functions of time, and we're only going to talk about scalar valued signals, but we do need to talk about time. So time will be a subset of R. And as such, time, there's two attributes of time that it inherits from the corresponding attributes of the real line in which we're primarily interested. Okay. So we, from R, time inherits two features. One is that it inherits a group structure. And the group structure, so R has, kind of, well, almost two group structures, addition and multiplication. For multiplication, you should omit 0. We're interested in addition here. And the other structure that it inherits from R is the order. Okay, so one time being greater or less than another time. Okay. So for 1, the set of times should be a subgroup of R. Okay. And so what are the subgroups of R? Well, here are some. The set of integers is a subgroup of R. So remember, I'm using here the additive group structure of R, and so not the multiplicative one. And so, the inverse of an integer is its negation, which is also an integer. And similarly, the set of rationals is a subgroup. And the one that's going to be of interest to us here I'm going to write as Z of delta. So delta is going to be some positive real number. And Z of delta is simply going to be the integer multiples of delta. Okay, and so this is the sampled time interval. Sampled time domain with sampling interval delta. Okay. All right, so the two that I'm actually going to be interested in here, the two subgroups of R that I'm going to be interested in are, this one, and well, not this one, but this one actually, all of R. Okay, so those are the only two subgroups that I'm actually going to care about. Okay, and so that's one sort of feature of time that we're going to think about is this kind of group structure. And so for our purposes, that'll be either R or Z of delta. And what we also want to do is we want to bound times. So also, and to bound times will sort of force times to be in an interval. And so let me kind of list the intervals. Okay, so these are the bounded intervals. There's 4 of them. So these are the real numbers between A and B, not including the endpoints, and so on. Okay, so you've seen these before, but I'm just kind of reminding you. And then there's the unbounded intervals, and these are these. So these ones are the ones that are unbounded on the right, and then unbounded on the left. And then unbounded on both sides. Okay. All right. Let's sort of pull this all together and talk about the notion of a time domain. Is a subset of R. Of the form and so we're going to denote a typical time domain by this symbol T, which is in the same font as my R. And T is going to be of the form of an intersection of two things. So S is going to be one of these subgroups that we talked about. Either Z delta or R, and I is an interval. Okay, now there's various attributes of time domains that obviously come out. One is, the dichotomy between the two choices of S. Okay, and the first choice is for the sampled time domain. We say that the time domain is discrete. Okay, so we talk about discrete time. And then the other possibility where S is all of R, we talk about continuous time. Oops, sorry. Okay. And there's other kinds of attributes that you could think about putting on time domains, and let's mainly just talk about one. So if I, the interval I, is bounded, then we'll say that T is finite. Okay, and that does not mean that T is finite as a set. It does if it's discrete. Okay, but certainly if we're in a continuous time domain setting, and the interval I is bounded, well, then the time domain is simply just the interval, and certainly as a set, it's generally not the case that T is finite, but we'll say finite time. So in the sort of colloquial use of the word finite time. Okay. Okay, good. So that's what time is. Let's talk about now the thing of interest to us, which are signals. So signals, as I've said already, is just a function of time. Okay. All right, and so as I said, we're going to focus only on in this course on scalar valued signals. In the companion course, we'll talk about vector valued signals, finite dimensional vector valued signals. Okay, and signals can have various attributes, of course. A signal is continuous time if T is continuous and discrete time if the time domain is discrete. Okay, so you should be careful here. To distinguish between a signal being continuous and a signal being continuous time. Okay, so continuous time has to do only with the domain of the signal, and continuous, well, let's think about continuity for a moment. In the discrete time case, it turns out that if you think about what continuity should mean, in the discrete time case, every signal is continuous according to some definition of continuity that I'm not going to talk about. And so continuity, the point is really an attribute of continuous time signals. signals. And so you can certainly have a continuous time signal that is not continuous, and we will be interested in those. So be careful to understand the difference between those two things. Okay. All right. And so we are, as I've already said, interested in vector spaces of signals, continuous and discrete time. Okay, and so what we're going to do to get started talking about that is we're going to talk about vector spaces in a not really general way, but in a different way, certainly than a different focus than what you've seen in your sort of standard linear algebra class, where really the emphasis was on finite dimensional vector spaces and, you know, sort of the structure of finite dimensional vector spaces, bases, and stuff like that. We're still going to be interested in some of those things from that linear algebra course, but the difference is here we're going to be focusing almost exclusively on vector spaces that are infinite dimensional. Okay. And so we're going to do some linear algebra, but it's going to be pointed in a very specific direction. Okay. And so I'm going to assume that you know what a vector space is. A vector space, you know, is a set with two operations, addition and scalar multiplication, and then those should satisfy a bunch of properties. There should be an additive inverse. There should be associativity and distributivity properties among the vector space operations. And commutativity properties. So I'm definitely not going to list those here, but I do assume that you know them. For the purposes of our discussion of linear algebra, I'm mainly interested in sort of thinking about some examples in an appropriate way for our purposes. Okay, so the first example we'll think about of a vector space is the standard one, the standard finite dimensional vector space, Fn. And remember what this is that this is the list, ordered list of n tuples of numbers in F. Okay, so every finite dimensional vector space is isomorphic to this one. And this has vector space operations, and I'm going to write these down because we're going to look at this vector space in a different way shortly, and it'll be useful to have these operations explicitly written down. And here's how you add two vectors in Fn. You add them component-wise. Okay, and similarly with scalar multiplication. Okay. All right, and so this notion of, you know, component-wise is going to be one which we will understand in a slightly different way in a second. All right, so this is a very simple finite dimensional vector space. Let's look at another vector space, which is not finite dimensional. It's still, I guess, simple, depending on how you look at things. And that is the vector space C0 of, and here I'll just talk about functions on the interval 0, 1 with values in F. Okay, and so this little bit of notation here is going to be important for us, okay, because we're going to be introducing lots of classes of signals And it's going to be annoying for you to sort of keep them all in mind. And my notation here is designed to help with that. So the idea here is that I have these parentheses, and then inside the parentheses, I have two things separated by a semicolon. And the first one is the domain. Okay, so these are functions defined on the interval 0, 1. The second thing is the codomain. So these things take values in F. And then I'm going to have some decorations out front, which tells me the properties of the signals or the functions that I'm talking about. And here C0 means continuous. So, sometimes people just use C here. The 0 is meant to disambiguate this from another scenario where R might lie in sort of non-negative integers, and when we'll see this later in the course. And so the idea is when R is equal to 0, it means continuous. When R is equal to 1, it means continuously differentiable. So C1 means continuously differentiable. C2 means twice continuously differentiable, and so on. And C infinity means infinitely times continuously differentiable. Okay, so the 0 here is meant to distinguish from, well, not 0. Okay, so these are continuous functions on interval 0, 1. Okay, and what's the vector space operation? Well, you know what it is. You know how to add functions, but let's write it down. So if I take two functions f and g and I add them, I should get another function back. So it's going to want to take values at some point x in the interval 0, 1, and the way you add them is the obvious way. And similarly with scale and multiplication. Okay. All right. And so, in defining this addition and scalar multiplication, there's something you have to actually prove, right? Not just the vector space axioms, which you also have to prove here, but you have to prove that under this definition of addition, the sum of these two functions f and g, if f and g are continuous, then the sum is also continuous, and similarly scalar multiplication. Okay, so that's something that you did in your analysis course. Okay, let me look now at another example of a vector space. And this one kind of, in some way, interpolates between these two examples, okay? So it's like this one in the sense that it's a vector space of functions, but it also includes this one as a special case, where this definitely doesn't include that as a special case. Okay, good. So the definition, as I'm going to give it, is going to be quite general, and then we'll look at some special cases. So I'm going to take a set J, any set. Could have finitely many elements or infinitely many elements. I guess it shouldn't be empty. F to the J then denotes any mapping F from J into F. Okay, so that's the notation I'm going to use for mappings from J into F. And there's general notation here of X to the Y for sets X and Y. This should be mappings from X to Y. So this is notation that's commonly, not exclusively used, but commonly used. Okay. And so F to the J is a collection of functions. It's the collection of all functions, F valued functions on J. All right, so this has a vector space structure, and the vector space structure is rather like that one. Okay, so the vector space structure is that you take two functions, f and g, and you add them, and the result when you add them should be a function on the set capital J. And so I'll denote a point in the set capital J by little j. And the addition here is exactly like in the continuous function example, like so. And similarly, scalar multiplication. Okay. And so this space is quite similar to this one in the sense that they're both classes of functions. This one is somehow simpler because you actually don't need to do any verifications except for the algebraic verifications to show that these operations define a vector space structure on f to the j. Whereas here, in the space of continuous functions, you have a little bit of work to do to show that the sum of continuous functions is continuous and the scalar multiple of a continuous function is a continuous function. Okay, so this is kind of a purely algebraic and has no analytical component to it like the previous example did. All right. Now I want to close my list of examples by looking at two special cases of the previous example. So special J's, okay? In the first case, J is going to be the finite set 1 to n, okay? And so here, I'm going to actually understand this space f to the j in this particular j as being something we already recognize. And I guess it shouldn't surprise you just by the existence or appearance of that n, that this vector space is isomorphic to Fn. Okay, and so I mean isomorphic is a vector space, and so to show one way to show that it's isomorphic is to define an isomorphism, so a linear mapping that's also a bijection. Okay, the mapping and so this mapping I'm going to call iota from F1 n into Fn. Okay, so this is going to be a mapping which takes an element here, which is necessarily a function defined on this set, and return to me a list defined in that space. Okay, so it's going to take a function f, and it's going to map it to, a list of n numbers. And if you think about it for a second, there's only one possible way to assemble the data that I have in front of me, which is this mapping f from 1 to n into f, and then this set itself, and then the codomain of the function f. There's only one way to assemble that data into n numbers, and it's this way. Of course, you could also do something stupid like take zeros, or you could change the order or do things like this, but this is the obvious way to do it. Okay, so I have a mapping. Okay. And this is directly verified to be linear. Okay. And to show that it's an you can show that it has an inverse, for example, and that's the way we're going to do it. You could use some facts about linear algebra to try to do this a little bit more slickly, but we're going to directly construct an inverse because I think directly constructing the inverse gives the sort of insight into what's going on here, and so moreover. Iota has the inverse, iota inverse mapping from Fn into f to the 1n given by, okay, so iota inverse maps Fn, so it's going to take a list of numbers, and what it needs to return to me is a function defined on that set. Okay, and so it's going to take a list of numbers, x1 up to xn. Now, the resulting thing needs to be a function which takes arguments from there. Okay, so let me take one such argument, j. And again, obviously, it's going to return the jth element of the list. Okay, and so you can just directly calculate by just composing the mappings that this is an inverse of that. Okay. All right, and so what this does is this kind of makes these two examples, which kind of don't seem like they're in the same class. It kind of makes, it gives a similarity between them, which isn't immediately evident, which is that both of these spaces are spaces of functions, really. Okay, this is a space of continuous functions defined on this interval, and this is a space of mappings from the index set 1 up to n into F. Okay. And so this is a space of mappings, and so it fits into the class of things that we're interested in. Okay, and now the other special case we're going to look at is where J is the index set of positive integers. Okay, so in this case, F to the j, with j being the set of positive integers, is it's a recognizable thing. So it takes the numbers 1, 2, 3, 4 and assigns to each of them a number, f of 1, f of 2, f of 3, f of 4. And what's that after all? It's nothing but a sequence. Okay, and in fact, by a real careful definition of what a sequence is, it's just by definition, it is the space of sequences. Okay, and so if you have a f, which is in f to the positive integers, this maps to the sequence f of 1, f of 2, and so on. Okay. All right, and so these examples are intended to illustrate that there's lots of interesting collections of vector space, lots of interesting vector spaces that are collections of mappings or functions, or when we go back to it, signals. Okay. All right, so we're going to continue talking about this next time.